So we will be implementing a binary heap in C. A binary heap is C structure, actually a binary tree, where every parent has 2 children. And what we are going to make sure in this min heap, like there's a min heap where the topmost element is the minimum, and a max heap where the maximum element is the topmost element. Sorry, the topmost is maximum. Now, what is special about this min heap, for example, we are going to implement is that we are going to always make sure that this element is the smallest. So actually we are going to make sure that every parent is bigger than both of his children. It doesn't really matter how these children like this are arranged, like 3, 3, 8, 5 or 2, 4, but what we should be sure of is that this parent is both greater than both of the children and this than both of the children. So what are the advantages? First of all, it is always sorted. You are sure that if you take this element, it is always the smallest. That's actually the only thing you're sure of actually. And every time you add an element or remove an element, you are going to do some things to make sure that this remains the smallest element. The advantage of this is that instead of having to compare every element to make sure everything is ordered as you do it in a normal array, like having your 1, 2, 3, 4, 5, 6 and comparing everything, you are just going to compare with, let's say, a single branch, like this branch for example. We should permit the operation to be faster, and even when the array will grow big in size, the more you will grow big in size, the less elements will be here. Like there'll be more elements, but I'll get it. You actually call it the log n operation. But whatever. Or log n. Well, I think you can just search about complexity. Complexity of a binary. So you are going to implement this in C using a flat array. So let me just create the C project. Create a binary folder, like my project folder, and inside my project folder I'm going to create a main.c where I'm going to implement my binary heap. So we are going to move with the code as we move with the algorithm itself. Includes stdio.h. We are going to use it for printing to input output and main. Wow. So, and then you are going to define a heap. You are going to have a simple heap of integers, and the size will be max size. You are going to define it as a constant 100. Voila. So max size will be the maximum size of the array. Heap will be the heap where you store the numbers. And look at something. We aren't going to store the numbers like in some complex structure. You are simply going to use an array where they are listed row by row. The advantage of using this listed row by row nature is that we can easily navigate within the parent of the children. How? We are going to look at a simple relation. So the index of the parent is simply the index of the children divided by 2. Like if this is, don't forget, in C we are using 0-based indices, so we need to subtract and remove 1. But in this case, for example, 2 divided by 2, 1, 3, 1, 4 divided by 2, 2, 5, 2, and that's the same. So to get to the parent, you simply divide by 2, and to get to the children, you multiply by 2, or you multiply by 2 and add 1. And that's exactly what we're going to do. So we are going to define that in functions. Define parent of n. We divide n by 2, as I just said. But as I just said too, for you to be able to divide by 2 to get the other index, you need to be in 1-base indices. Why in C we use 0-base indices? So we need to convert from 0-base indices to 1-base indices, meaning we add 1. And after you have add 1, we divide by 2, and when you divide by 2, we convert it back to 0-base indices. And let's not forget to put all of this in brackets. So what is this? Usually you use a function like int parent n is equal to all of this. Here I am using a macro. What it's simply going to do is that it's going to do like this max size. Every time you're going to type parent, like parent of n or parent of 5 or parent of I, you're going to replace it with the expression like this. The C compiler is going to replace it with the expression like this. You make that, you will not have to call a function, and you insert directly all of this expression inside your source code. So Sometimes it is faster since you does not have to jump between memory location between instructions. But you are not really going to expatiate on that. That's not the concern of this. And here you are dividing by 2. Something which is commonly done is to instead use bitwise operations like bitwise shift to the right by 1. You don't just understand that this bitwise shift to the right by 1 is actually dividing by 2, and bitwise shift to the left by 1 is multiplying by 2. That's also what you're going to do for the children. You're going to have child 1 to get the first child. You're actually going to do the same thing, except that you're going to multiply by 2 instead. You convert to 1 base indices, you multiply by 2, then you subtract by 1. Child 2 will be the same thing, except that you will add 1 to. It's like it will be the same thing as child 1 and you add 1 again. And you see that both of these ones will cancel and you're left just with this. So now you have the formula for getting the parent of element at m and both of his children. And let's not forget heap len. It is the current number of elements of in the binary heap. We are going to create 2 operations. Insert operation, which is going to insert an element, and pop operation, which is going to pop an element. So how do we insert inside this heap, making sure that this element is always the smallest? Sorry, that every parent is smaller than both of his children, because it's not only this topmost element actually. Okay. That's it. You are going to insert an element right at the end. This ends right here. Oh, grow bigger. Good. You are going to insert it at the end right here, and then you are going to shift it up, meaning you are going to compare with the parent. If it's smaller, you swap. If it's smaller again, you swap, and so on until it reaches where it's supposed to be. And that's exactly what you are going to do here. Void insert int m. Firstly, we insert it right at the bottom, but before inserting even, we need to verify that the heap is not too big. If heap len is greater or equal to max size, then there's nothing you can do, and you just leave it here. Maybe crash or print a message. Voila, let's print a message. Print f heap is full, and maybe exit with an error message. Voila. Let me include stdlib.h. I just included this. Heap is full. Or I think this is what we use in this case is p or heap is full, exit status 1. No, let me just use number printf. And return. Let's not make our whole program crash just because of that. So what do? We insert. Firstly, we increase the size of the heap len plus plus. We insert that element directly at the bottom of the heap, meaning heap at heap len minus 1 is equal to that new element, and then we shift up, as I just said. Shifting up is actually when you compare it with its parent and so on to make sure it is where it's supposed to be. We are going to quickly declare this shift up, and just like there's a shift up to compare with its parent, there's also a shift down to compare with its children. We are going to do that later. Instead of subtracting 1 here, what we can do is that we can instead use it before adding 1, like this. We set the last element to n, then we add 1, and then we shift up. You are going to define this shift up function. I think this will be one of the simplest functions to implement. You simply compare the last element with its parent, and then with its parent again. So the index of the current element will be, you store it in a variable n equal to heap len minus 1. Let's also make sure there are at least 2 elements in the heap. Heap len is, let's say, equal to 1. You don't need to anything. Size n is equal to heap len minus 1, and so on. Okay. Now you can even put that actually in a for loop, but let's make clear, while n is not equal to 0, meaning while we do not yet reach the topmost element. Actually, this even cancels this condition in one way. whatever. While n is not equal to 0, we compare the element with its child. Meaning if heap n, the element, is smaller than its parent, heap parent n, then we swap both of them, n and parent n. Let me put it in curly braces, and now the new n is actually the parent of n, because after you have swapped it with its parent, now you're instead here and you compare with its parent again. That's why I said this n to be that. And we need to define this swap function. We define a swap function which take two array indices and swap the element at those indices. We're going to make it simple and use a temporary variable. There are ways which do not use a temporary variable, like using XOR or adding them, but we don't want overflows or destructive operations, so avoid swap size. So you're going to notice I use what's happening here. You're going to notice I actually use size t instead of int for array indices. Size t is some kind of unsigned integer which have different sizes depending on your computer. It can be 8 bits or 7 bits or 4 bits, sorry. On most common, like here it should be 8 bits. And it is actually good for storing array indices, unsigned integer, or to store the size of an array. So we're going to have a temporary variable equal to heap a equal to heap b, and heap b equal to 10. As simple as that. Now you have a swap function and you have a shift up. Let's create a little function to make sure everything works fine. You create a dump function. We should print the array. Let's print it in a beautiful manner, like let's say 1, 2, 3, 4. I think this would be nice. So let me even create a document slash, what's that name again, binary heap. So something like 1, 2, 3, 4, 5. Wow. So let's see, you print the opening brackets, then you print each of the elements. For 5 t I equal to 0, I is less than heap is heap len, I think I plus plus. Then if the element is not the first element, voila, I greater than 0. Then you print a comma, because it is only this first element which does not have a comma before it. All of these elements have commas before them. As simple as that. And then you print the number itself, percentage t, heap I, print f, sorry, and then you print the closing bracket and a new line after it. Beautiful. Let's test our little heap. Insert a few numbers. Let's just insert numbers from 5 to 1. Voila. Int n is equal to 5, n is greater or equal to 0, n minus now minus. We insert numbers from 5 to 1, and then we dump the array to see how it looks like. What is important is that the topmost element, the first element, should always be the smallest. Let me run this tcc. So let's check this. 5, 5, 3, 2, 1, 0. Perfect. The first element is always the smallest element, because every time we insert an element, we compare it and put it up where it's supposed to be. And you actually see the power of a binary heap. If you look at what I did when inserting and when shifting up, I did not compare with every element in the array. I simply compare the element with its parent, and then compare that parent with its own parent, and so on. Oh, something. If it is less than the parent, you do this, else there's no need to continue. You can just break a loop. And that's its power. I do not compare with every element in the array. I simply compare with its parent, then its parent, then its parent, and that's what makes it fast. Now we are going to implement the pop. The pop function is simply taking these topmost elements. So how is this done? This is a bit more, less easy to implement. I will not say harder, less easy. What you do is that we remove the element here. You don't actually remove it, but you take it, store it somewhere, because you're going to return it. It's the topmost element. You take the last element, you put it in its place, and then this lastmost element will surely be bigger than this one here. So now you instead shift down and put it lower it's supposed to be. Every time you compare an element with its children, you compare with the smallest of its children. You understand the reason why? Yeah. Simply because if you compare with the biggest of its children, it could be bigger than this but smaller or equal to this, so it won't work. That's why you need to compare with the smallest of its children to make sure it's where it's supposed to be. You want, and if it is smaller, you swap. So you need to be smaller than the smallest of both of these before you swap. Because if this, for example, was a 2 and this was 3 and 2, you compare this with the biggest, maybe just like that, and you have 2 2s here, and yeah, it will be good. Actually, in this case, it will be good. Well, sorry, I'm just lacking cases to explain this, but I think you got the point. So let's implement that shift down. I'm going to implement it just here. By pop. Sorry, it does not return void, it returns int the topmost element. The number we're going to return, you firstly take it. You are going to assume that here that the heap is always had like one element when you are popping. If it doesn't have one element, then this heap will simply store a random value or a value which was not cleaned. As simple as that. This is the number we are going to return. Then we are going to start shifting down. Size t n is equal to 0. We start with the topmost element. So while we are going to put here 1 for now, or let's just say while n is less than heap len, voila. This actually is not very useful, but let's just keep it. While m is less than heap len, you will look for which element between the element itself and both of its children is smallest. If the parent is the smallest, there's no need to swap. If the left child is the smallest, you swap with the left child. If the right child is the smallest, you swap with the right child. As simple as that. So smallest, or let me just say small, is equal to n. We take the smallest to be the parent itself for now. Now we compare with its children. If the first child exists, why am I saying the first child exists? For example, this one does not have children. So you need to verify that if he has a children, then his child should be inside the array, inside the heap, and not be undefined. Like, should actually have a child. If child 1 is less than heap len, and the element at child 1 is actually less than the element at heap small. Sorry, I don't compare with n. You are compared with the smallest element. You'll be n, but you understand what I mean. So if child exists and the element at index child 1 is less than the current parent, then we need to swap them. Sorry, then the smallest is instead that child. That's what I need to do. We are going to see the two actually pretty much the same thing, except that instead of child 1, we are going to have child 2. And actually just the same thing. If the child 2 exists and it is current than what we know is and it is smaller than what we know is the smallest element, then instead the smallest element is child 2. So you are just looking for the smallest element. Once you have gotten the smallest element, if that smallest element is actually, if the smallest element is not the parent itself, it's not equal to n, then you need to swap the smallest and the n, and the new n will be the smallest element. Meaning, if for example this child was the smallest, you swap, and now you come to this child. That's why we said n to be that smallest element. But else, if the smallest element was actually this parent, it means everything is okay, and you can just break. That's it. Oh, what am I even doing? I'm confused algorithms. This logic actually here is the sift down logic. Sift down. Voilà. And that's how you sift down. And before sifting down, just like here, you verified you should have some more than one element in it. We do the same thing here. And let's create our pop. In pop, we are going to use this sift down. I told you, firstly we connect the element we want to return. We exchange the first element with the last element. Sorry, heap len -1. You can then move one element from the heap. Remove, like, mark that the size has reduced of 1, and then we sift down. This is actually how the pop does, and return ret. So remember what I told you the pop does. You remove this element, you exchange this element with the last element, and then you sift it down. That's exactly what you do. You remove this element, you exchange with the last element, and then you sift it down. Instead of subtracting 1 here and subtracting 1 from heap len, we can just put it here when you have already subtracted 1. I think this is better. And we have our pop. Now let's write some tests. We don't need this dump again, or maybe you should just keep it for the benefit purposes. Whatever, let me keep it somewhere safe. Voila. You are going to insert elements from 5 to 0, or let me even say from 10 to 0. Voila. And after I've inserted the elements, you will sort them back. Actually, pretty much this logic, but you are going to print f %t pop. So firstly, we insert elements in reverse order, and then we pop. And we always make sure and we try to test if this pop is working well. Every time we remove the element, we should remove the smallest element, so we should remove them naturally in order, even though we inserted them in disorder. So 0, 1, 2, 5, and it is in disorder. I actually have an issue with my code. Oh, how sad. So let's try to do like this. Temp is equal to heap A is equal to heap B is equal to temp. This is okay. See, the error will likely be inside this sift down. Pop red is equal to heap 0, heap len minus heap 0 is equal to heap len if heap let's get to 0. Minus heap 0 is equal to heap. Oh, this is something. We are replacing it. No. I already subtracted once, so there's no need to do that again. So let's use the sift down function. Size n is equal to 0, while n is less than heap len. Smallest element is currently n. If child 1 n is less exists and heap child 1 there's an issue here. Yeah, there's an issue. Should I do that even? No, I'm not doing something right. But I think there's something here. If the child of the current n is less than heap len, yeah. Oh, what's happening to me? If child 1 n is less than heap len, yeah. if the first child exists and the child of the smallest variable, yeah, whatever, in this case it will be small, but n and so on are the same, so it's chosen this step. And in this second case, if child 2 is less than heap length, yes, and heap child 2 small, yeah, we are instead comparing with child 2n, so let's do it here too. It's less than heap small, then small is equal to child 2m. Yeah, this is how it's supposed to be. If small is not equal to m, and if the smallest value was one of the children, then you map it with one of the children. Let's try to view like this. Oh, and actually that was the issue. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and everything was fine. Good. I won't count how much time it took me to debug that. But well, we implemented our data binary heap. We kept things sorted. We could actually try to view what happens. Let me put back the dump function. Let's just try. We insert 5 elements, and every time we pop an element, we dump the array before printing. Okay. Voila. So this was firstly array. We popped 0, then it gives us this array, and you see year 3 is right at the bottom. It climbs up, and here it climbs up again, and here it climbs right to the top. So you see, the more we actually use the array, the more the things order themselves. That's actually nice. It doesn't make sure the array is exactly as ordered right from the beginning. It just maintains a little order by comparing some things, and wow, that's impressive. Thank you.